Okay, Bismillah ar-Rahman ar-Rahim, wassalatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. Okay, let's continue the lecture about support vector machine. And yesterday we talked about maximum margin classifier. And the maximum margin classifier basically means that we need to find the boundary H1 and H2 that maximizes the margin between these different points, okay, to separate them into two different separate classes. And of course, this is possible when we have points that are linearly separable, like in this particular case. And we define the distance, the concept of the hyperplane, the gutter H1 and H2, and also the equation of the distance. So I hope that yesterday you already made the different questions to apply these concepts. Okay, so this is how we calculate the distance. It's basically the absolute value of the decision function divided by the norm of the vector W, the vector of the weight. And today I'm going to provide illustrative examples on how we can do these calculations. Sorry? Yes. Yeah. For the distance, yes.
So this is for a single point.
No, this is a vector, not only for a single point. This is a vector representation. Okay? So W here, it's the vector of weights. Okay, and X, it's the feature vector. Okay, and this is how we calculate the distance. This is, these are known formulas in linear algebra to calculate the distance, the perpendicular distance between a point and a line. Okay? And at the end, we came up to the conclusion that the maximal margin classifier in SVM is basically to minimize or to maximize the margin, which means minimize the norm of the weights that we look for. So we're going to find the weights Wi such that we minimize the norm of the weight, which is the square root of the sum of the squares, the weight of a vector. But this is not an unconstrained optimization like in typical gradient descent. This is a constraint optimization because we need to make sure that every point is outside of this particular margin. I'm going to explain today why we need this constraint in all details. And finally, we can solve this problem. There are different ways on how to solve this problem, this optimization problem. One of the ways is to use gradient descent with the constraint that you've mentioned. And okay, so this basically means that we need to minimize the hinge loss for all the different points. So in order to understand all of this, I know SVM is a little bit tricky topic, and you need to understand the concept of the hinge loss to understand how the minimization is done. So let's look at the hinge loss. So given a particular scenario like this, we want to calculate the hinge loss, and this time for a misclassification case. So this is our vector W. What does it represent, W and B? Okay, it represents our hyperplane. So this is basically the W plus B represent this line. Okay, that captures the relation between feature 1 and feature 2. Okay, and we have the bias. Now, given this point, x02, which is this one, I would like to calculate the loss, the hinge loss. So we're going to apply the formula. And I'm going to consider that I have a misclassification. So look at this point here. What is the classification of this point? Positive or negative? Positive. Now imagine that you've made a model that provides yi, you're making the training, and yi is negative. So here, in principle, what kind of loss we should have? 0 or higher than 0? Higher than 0. And now we're going to calculate to see how the hinge loss actually works. Okay, so this is the equation of the hinge loss. Given you have a point xi, and you have its label, I want to calculate the loss as follows. It's max 0, yi, it's minus 1, and here fxi. This is the transformation. Okay, so what is fxi?
f of 0, which is 2.
It's basically we need to apply the decision, calculate the decision function fxi, which is basically this one. We're going to apply this linear equation to see whether it is above or below. So this function is going to give us a point, okay? So a certain value here. Okay, so doing the calculation, we find that fxi is equal 1.80, which is this one, 1.118, 1.12. So that's the value. Now I have this one, so I'm able to calculate the hinge loss. One of the exercises yesterday actually asks you to do the following. So how to interpret this one now? Let's anticipate on the loss. Now this tells us that this is a positive class because it has a positive value. Okay, and it is greater than 1, so it means it lies outside the SVM margin. So it's either here or here, so it is here. Okay. So this is the fxi here. And my classification says what? -1. It's different. So the fxi gives, look, fxi, it's independent of the prediction. So it's just the value that we calculate based on this line. So based on this line, the prediction is positive. But I made here that my value is negative. So let's calculate the loss. So given all of this, we calculate the loss by applying the formula. Okay, this formula. And here we apply -1 multiplied by 112. So what will be this value? Yeah, so it will be 2. So we have minus, so this is plus. And this is going to be 1 plus 112. So at the end, I'm going to find this one. So this is my hinge loss, 2.118. So this value, what does it indicate the loss? If the loss is not 0, it means that there is a deviation. And the deviation here is big. It means that the initial value here, it's misclassification. Okay, because the loss here is high. So this value indicates the degree to which the data point violates the margin. And indeed, when we look at the point here, it's below the SVM margin and it's classified as positive. And this classification here is negative, so it's wrong. And this is why we had a hinge loss that is high. Let's now assume that we have yi equal to 1, a positive value. Okay, and look now, even if we apply the method you predict, SVC predict on the new data, if I provide 0 to point, it's going to give me the class 1. So that's the good prediction. And now let me change yi to 1 and we calculate the hinge loss again. Okay, so applying the same thing. So of course, the decision function is the same. It doesn't depend on the predicted value. Okay. And now calculating the hinge loss, applying the same formula. Now we will have 1 instead of -1, so it's going to be 1 minus 1.11.8. And this is going to give us the max between 0 and the negative value. And look now the hinge loss, how does it work? If you have a negative value, it's going to make the loss to 0. And this we call it the hinge. The hinge yani mafsal. So it's going to cut the loss at certain point. If you go to a negative value, it's going to cut the loss at a negative point, and the loss is 0. And this is very natural. Okay? Now, the hinge loss becomes 0 in the second case. This is for the old graph. Okay? And it makes a lot of sense now because I have correct classification. So the hinge loss is 0 because the predicted is equal to the ground truth or the actual value. So this is how the hinge loss performs. Now I'm going to take another point, 0, 10. So 0, 10, what will be the correct prediction? Minus 1 or 1? Minus 1. It's in this area. Okay. Okay, so the loss is 0 means that the classification is correct. And now taking this point, and we want to calculate the hinge loss again. So I'm going to apply the same functionalities. Applying minus 1 as the prediction. So calculating the fxi, by applying this formula, I will find that fxi is equal to negative 1.9. And this gives me a negative value. It means that the classification is negative. So I'm going to classify this as minus 1. Now we apply the same thing. We apply the hinge loss. Okay, the max between 0 and minus 0.9. So same thing is going to be equal to 0.
Based on what do we see the YI?
The YI, it's an example of a prediction. Imagine that you do the gradient descent. So you're going to have random values in the beginning and then generate a loss. صح ولا لا? Okay? So if, for example, your random value generate minus 1 or any value, not necessarily minus 1. Okay? So based on this, we're going to calculate the loss. If the loss is 0, there is no gradient update. If the loss is different from 0, we're going to use this error to update the gradient.
So when you do WTXI plus B, this is not the prediction.
Which one?
When you apply WTXI plus B.
It gives a prediction, because when it gives minus 1.9, it means a negative value, so it will classify it as minus 9. It's similar to when we have in logistic regression, when you have a probability above 5 or below 5. 0.5, sorry. So you're gonna map it to 1 or to 0. Okay? So here, if you have a negative value, you're going always to map it to minus 1. If you have a positive value, you're going to always map it to plus 1.
But if you go to the example before, we choose that YI is positive, but the prediction is negative.
Here. Where? Here?
When you found the loss was...
Yeah, because we have the point here. Look at the point.
the one I think before.
Before, okay. Okay, yeah. This point here, it's plus 1. This one. It's plus 1, and they consider it as minus 1.
Yes.
So look at the loss now.
It's positive.
It's positive. And makes sense.
But
Because we have a misclassification.
now YI is negative 1, but the prediction, which is the WTX, is positive. So how do you get YI?
Repeat your question.
The f of x.
F of...
Yes.
Yeah, this is f of x. 1.1.
Is it the classification?
Yeah, this is like the classification, yes.
So when
No, because here we have the correct. Look, here I already determined the value, the correct model.
So YI is the correct value.
This is
Classification.
this is like, I understand what you mean. I just wanted to show here in this example when you have the ground truth. Okay, now I imagine that I have the ground truth, and of course the ground truth I obtained it from the model.
So assuming
I assume that I have a data set that has the ground truth. Okay? And now I would like to calculate the loss. I wanted to explain to you how the hinge loss function. Okay? And this actually will push me to show you the curve for the hinge loss. And we call it the hinge. This is the hinge point, by the way. هو المفصل. Okay? Look, the hinge loss now for y negative. What's going to do? It will be 0 for any negative value of the decision function. Because if you get a negative or a value smaller than minus 1, it's going to be mapped to the minus 1 class. So the loss is going to be 0. And for any other value above, so it's going to increase linearly. Yes. And this is similar to the ReLU function that we use in neural network usually. It's a function similar to this one. Okay, now if we look at the hinge function for y equal to 1, it's going to be in the opposite direction. Okay, So it's going to be 0 for values greater than 1. And we'll have an increasing slope for the values that are smaller than 1. Okay, and this is the hinge loss region, which is in gray color. Okay. That's about the hinge loss. Now we're going to talk about the constraint optimization. Okay, so we have yi, there are labels between either equal to -1 or 1, and we have a classification condition. What is the classification condition here? If we consider only the line, this line, okay, so we classify, the classifier assigns the class 1 if I am above, okay, if the decision function is greater than 0, I'm going to classify as 1. Forget about these two lines. Consider only this one. تخيل ما عندناش المارجن. Okay? If I have a point here, what will be the classification? 1. And the point here? -1. So that's very clear. This is what we call the classification condition. But in SVM, we don't only consider this one, we want to have a margin. And when the margin is very large, so we have less likelihood of misclassification. And this is why we want to maximize the margin given the points that we have to avoid misclassification. But you know, just the classification condition is that if you are greater than 0, you're going to assign it +1. If you are smaller than 0, you're going to assign it -1. As simple as this. So this will be like the cutting line between the two classes. So this value here is going to be classified as negative. This value also will be classified as negative. So regardless of H1 and H2, this value will be considered as positive, positive, negative, and so on. Okay, so, and we can write this formula as yi multiplied by this one. It's always positive. Make sense ولا لا؟ إذا كان yi negative وهذه مش تكون negative تكون positive. وإذا هذه positive هذه positive تكون positive. So these two conditions they can be replaced by one condition.
I don't understand the transpose of W.
This?
Yes.
Forget about it. It's just a way to, if you don't transpose, you're going to have a computation error. That's it. عندك vector هكذا و vector هكذا. You need to transpose to get a value.
طب بالنسبة وش W?
Consider Wx. W is the weights that you learnable weights. هذه الآن we will learn its weight. It's the weight of this function. مش عندنا W1 x1 plus W2 x2 plus b. We're going to make it in a compact vector format, which is Wx, forget about the transpose, Wx plus b. And W is something that you can compute with x. Clear? Okay. Is this clear? لأنه هذه باش ندخلكم بعد للsoft margin classifier. We need to understand this one. So, do you understand that these two conditions can be replaced by this condition? Good.
But that doesn't bound to the H1 and H2.
Yeah. Now, this is the classification condition, but it's not the margin maximization condition. What is the margin maximization condition? If I classify correctly with respect to the margin, what's the correct points that are classified here? With respect to the margin.
The closest one to the
Is this point correctly classified? This one?
No.
No. This one? No. So in order to be -1, it has to be below -1. And if it is +1, it has to be above +1. And I should not consider this one. So my condition, instead of being greater than 0, what it should be?
This -1 and greater.
Yeah, يا اما اكبر يا اما greater than 1 ولا smaller than -1. So these points should not be in the classification of maximum margin classifier. And this is why we can write this condition.
This is only for the. Oh,
This replaces the two conditions, -1 and 1. Same thing. We're going to have values greater than 1, either negative by negative or positive by positive. So in this case, we will make sure that our classifications are outside of this street. And the larger the street, okay, the less issues you would have of the conflicts between the two classes. So this is the condition that we need to have for the maximum margin classification. And this is the constraint that we will use when we want to minimize the norm of the vector. We work with constraint optimization. Yes or no? What is a constraint? What do we want to minimize? The norm of W. Constrained on what? Okay, the norm of W, it can lead to provide you these classifications. But in this case, we will say we're going to accept only those points that satisfies this condition. Okay? So this will discard these points from being correctly classified. So this is more restrictive. So this condition ensures a correct classification with respect to the maximum margin classification, okay, and will ensure the maximum margin between both. So maybe in this case, if we're going to optimize, we're going to have the lines at this level, maybe at this level and at this level. So the street will be much smaller, okay? And this is if you want to use maximum margin classification. But usually, if for example, I don't allow these classifications, if for example, I don't allow this classification, what will happen? I need to shrink this margin too much. Okay? مثلا تولي قريبة جدا, تولي very close to the H0. H1 and H2 will become very, very close. It's only because these 2 points. So in practice, we say, okay, let's ignore these 2 points. Let's allow to have misclassification in order to have a better margin. So now I can play with the margin to be very small. If I'm very strict, I will take only the maximum. Okay? Or I say, okay, I will try to increase it. But increase it to which level? Now that's the question. And here we play with the hyperparameter. واضح الإشكال ولا لا؟ Now, if you want to apply maximum margin classifier, you need to change H0 and H1, and they will be very close. So it's almost, you will go back to H0 as a classifier. But if you say, okay, I can allow some misclassification by allowing a margin similar to this one, and in this case, we're going to do what? We're going to remove a certain value that we call Xi, which is called the slack variable. And look, for example, if Xi equal to 1, it's like I'm having this greater than 0, so it's basically I'm only shrinking the line to H0. واضح?
Doctor, what is this sign?
Which Xi, it's called Xi. Xi.
It's a variable?
It's called the slack variable, and it's a learnable, it's like a learnable tolerance. I'm going to explain this in a while. لكن من حيث المبدأ, from the concept perspective, if I remove a positive value, it's like I'm going, for example, imagine that this is going to be close to 1. It's like 1 minus 1, so greater than 0. So it means I'm going to take the hyperplane as separating, yes. So I can shrink too much the margin, or if this value is going to be, for example, high, okay, I can also extend the margin. I'm going to show you a demo about how it works. So this Xi is considered as the constraint violation degree, to which extent I can violate the constraint of the margin. I can tolerate to have misclassification. And this brings us to the soft margin classifier, where we cannot have clear, linearly separable data. Just it's because of the noise, but not for another issue. So in the soft margin classifier, if we have something similar, we might have data that will be necessarily misclassified. Okay, similar to this one. So in soft margin classifier, we will allow outliers, okay, in order to have the best possible margin that will provide the best accuracy possible for the SVM classifier. Okay, so at the end, it's an optimization problem in order to find the best margin possible. And for this, okay, let me remind about the maximum margin classifier. This is what we want to optimize. We want to minimize the weights, the norm of the weights, subject to having this product is greater than 1. Now, if we want to apply this in soft margin classifier, okay, we're going to add the constraint minus xc. So this is basically a learnable tolerance, and we will introduce a new hyperparameter c that will introduce what we call the regularization term. And you know what is regularization. So regularization, it means, what's the role of regularization usually in data science? Reduce overfitting. Reduce overfitting, it means it will allow some misclassification on the training for better generalization. So I'm going to allow some of the misclassification to have a better generalization, so I can have a margin not really 100% fitting, almost perfect for your training, but no, it's going to deviate a little bit from the training to be more general. Look now, if for example I want to make it perfectly to the training, I will make this one much closer to each other, but it doesn't generalize very well. Okay, so in this case, this margin will provide a better generalization, and here we have a C factor that represents a hyperparameter, so it's a parameter of your choice. You will change it in order to find the best classification accuracy possible based on the data. Yeah.
You said that we want to maximize the margin.
We want to maximize the margin that provides the best classification. Okay, I can maximize it completely.
But
just remove it.
within the constraint.
Within a constraint, yes.
Now let's say I'm testing the model I just created, and I find the point in the margin.
Yeah,
Still gonna classify correctly.
yeah, you're not going to look at a point, you're going to look at an average classification report. Like the precision, the accuracy, you know, these parameters that we've made in the classification called the recall, the F1 score, same thing applies here. Okay, you can run the whole classification report on the SVM to check whether your points are correctly classified for 80%, 90% of accuracy, precision, recall, and different type of functionalities, metrics, sorry. Okay, so, you know, in the max margin classifier, we minimize only the norm of the vector. In the soft, we're going to have a regularization term that will consider a hyperparameter, C, okay? And this is subject to minimizing, subject to the constraint, this product is greater than 1 minus C for every feature vector. And C is the regularization hyperparameter, C is the regularization hyperparameter, so it's a parameter of your choice. And C is the slack variable, and it's learnable. It's not set in advance. It's learnable. It's not a weight, but it's kind of a tolerance that will make the model deviate from the perfection to be away from the overfitting. Okay. So look at the effect of the regularization term. Let's see this video to understand. Here I'm going to make, this is a Python script that will show you the margins for different C vectors. C values. Look, let me start from the beginning. Look, the first value, something very, very close to 0, okay? And then when I increase, the margins, okay, are going to be more bounded. Look, enter a certain value. This is the effect. So it's a hyperparameter. It's up to you to decide where to stop. Look, it's going to stop here. And now we're almost at the maximum margin classifier, the most efficient one. Of course, in this particular case, I didn't have outliers. I could have added some outliers in order to have better effect. Okay, but look, beyond this 0.0, look, beyond 0.5, it reaches the best possible margin. So it couldn't even go smaller. Okay, but for very small values, when we ignore the regularization, what does it mean small value? C is equal to 0, I ignore the regularization. I'm in the other case, only optimizing this, the norm of the weights. Okay. Okay, if I ignore that. So this is how it works. So this is the impact of the regularization parameter. And this is a summary. So if we have high C values, this is going to minimize the error. And low values, it will maximize the margin. The margin is going to be bigger. Okay? And bigger, what does it mean? It means more simple model, it's a simplistic model, and avoid overfitting. So we're going to need, again, is the trade-off between the bias and the variance. شفت هذا أهم شيء في الماشين learning, the bias variance trade-off. Is to get the base trade-off. واضح? So don't worry if you don't pick all the, this is one of the most typical topics, by the way. So the most important thing is you understand holistically this SVM. You're going to have to learn it again in machine learning course. لكن الأساسيات موجودة الآن بالنسبة للماشين بالنسبة لل. I will finalize by the final trick. I've given you this video, so you can see it. طبعا we need to go into higher dimensional space, but just to summarize, the three kernel functions or kernel trick. So the core idea is to transform the data into higher dimensional space to enable linear separation. في بعض الأحيان مثلا أشياء مثل هذه we cannot have a linear separation. Okay, so this is why we call it the kernel trick. So kernel is basically a function that we will apply on the relation between the data points. And we call it a trick because usually we don't do the transformation, because the transformation, for example, if you apply a polynomial transformation or an exponential transformation, is going to make computation more difficult. So the idea here is actually to use these transformations on investigating the relationship between the data points. And let me explain this one. So basically, if we don't use any transformation, like if I do the following one using the traditional technique, is a linear kernel. So the linear kernel is going just to see the relationship between the points into the same dimensional space. اللي سويناه كله linear kernel. Everything that we've done so far, it's just a linear kernel. We work on the same dimension. Look, linear kernel facilitate linear classification on the original feature space. We don't change the dimension. Okay, that's the kernel. مثلا الآن, if I have these data points, I apply linear kernel, so it's basically the standard SVM. I'm going to have this separation, and it's going to give me 65% of accuracy. Standard SVM. Okay, and now in Python we apply kernel equal linear, and C equal to 1. C is what? Is the hyperparameter for the regularization factor. We can apply polynomial. Look, this is polynomial at degree 3. What does it mean? So what is the accuracy now? Better or smaller? So look, it's a more complicated curve for the separation, but it's so complicating the model doesn't mean that we're going to have a better accuracy. Okay, and this is the polynomial kernel. So basically, if we have a quadratic transformation, the kernel will be 1 plus the dot product multiplied by 2. So this is R, and this is the dimension of the polynomial. So this is a polynomial of degree 2 in this particular case. And here we have 3. Look now, I changed the D to 10. Okay? Now we have a better accuracy. Look now, it's more complicated curve for the H0. And it provides a better classification. Look, it separated this cluster from this cluster, this cluster from this cluster, and here I have something in between. This is what reduces the classification accuracy from 100% to 72%. And of course now, for example, I tried even D equal to 100, it give me the same thing. لأنه 100 maybe مش يتوقف هو في 10 ولا maybe حتى في 8 or 9. So sometimes it reaches a certain degree, it's going to stop even if you increase the degree of the polynomial. And the last one is the radial basis function, RBF. And this one is more complicated and more accurate and can actually feature higher dimensional space using the exponential function. And look now, it provides fitting to a very complex pattern. Okay, so it's able to identify the patterns in a more accurate manner. Look, it made a fitting here, here. So it completely separates. Now, if you look at this curve, you see it's almost difficult to separate the two classes with the function. But using SVM with the RBF kernel, we can find a good separation between these data points using this function.